Yes, good morning, everyone. Thank you for the introduction as well, and welcome to my talk, Property Testing Julia Code, or, well, at least how I learned to love randomness. And maybe let's start with a little bit more about me. I've been writing more or less buggy code since about 2010. I don't remember writing code before 2010, so that's why I say, okay, that's when I started writing buggy code. I've been a Julia user since about 2016. Studied software engineering at the Technical University of Vienna. I'm currently at TT Tech Auto AG, and all of these opinions here are my own. I'm here on my own time. And in general, I'm interested in software correctness, low-level programming, compilers, all the nitty-gritty stuff that is necessary for us to do our work. And before we jump into the difficult bits and topics, there's a few questions to you. Don't worry, you do not have to study anything. They're very simple questions. It's just an audience survey. First question is here. Just raise your hand. Who has written buggy code? Well, okay, good. Everyone's very honest here. And who has debugged that code? Maybe not so successfully. Yeah, it happens, right? So this is something that we all know. And maybe the most interesting question from my side is, who has written correct code? And if so, to what degree? Decision coverage, anyone know of this term? Okay, there's a few who know this, but it's difficult, right? So yeah, this is where we're going in this direction. We're not going to get to completely correct code, and well, it's completely difficult to do this. So let's go with an overview first. At the beginning, we're going to say, what even makes a bug? How can we somewhat reliably identify, okay, this is what I would call a bug? Then we can look at one example where we can say, okay, we have some documentation. How can we extract tests from this documentation just purely on what the function says about itself, decide this is what we actually, what we're interested in. Then we're going to look at a second example of something that's a little bit more complicated, where we can say, okay, we have some mutually dependent functions that are inverse of each other, and how can we test them together maybe and learn something about that. And finally, we're going to have some conclusion and some future knowledge view. And I hope by the end you're not too depressed about it, but it will be, I think, a well-earned learning experience for all of us. So let's dive right in. What is buggy code? Is it buggy code when a user opens an issue? Probably not, right? We have some issue template, the user reports an error, and sometimes this error is completely expected. And this is not necessarily something that is always a bug. Is it a bug when a test fails, when nightly fails, or a new feature branch fails? No, we may have gotten the test wrong, and even if the code is wrong, it's not necessarily indicative of an actual bug that we have introduced now in the existing code. Maybe it's when we read the source code and notice something that's a little bit odd when we say, okay, we want to analyze and debug this code, but here too, we can't necessarily say, yeah, this is definitely a bug, because we may have misunderstood something. And well, the only reliable or somewhat reliable way of identifying bugs I've seen so far and have encountered and what I've settled on is, well, there's some mismatch between what the code actually does and what we've seen in the documented expectations and what we expect from just reading our documentation. And you see this asterisk down there at the bottom, because sometimes we intentionally don't document things, right? Sometimes things are not relevant for a user, but nevertheless, they should be documented and written down somewhere in the dev documentation, because in 2 years from now, we maybe come back to the code and then we don't remember what it does. We look into Git log and see, oh, it was us who introduced it, and we ask ourselves, what have we done then? So with this information, let's maybe look at a small example. I want to stress and mention the examples I show here are not meant to point any fingers anywhere. It's just, these are good examples, so that's why I chose them. So who of you knows the floor division function from base Julia? Probably some people know it. And it very simply states that it returns the largest integer less than or equal to x divided by y. It sounds reasonably simple, right? We can even copy paste the entire function definition, which comes from the free argument diff function down here, and so we see, okay, it's one line of code. It looks really simple. We just from our first argument subtract the remainder of the division, divide again, and finally round. This looks simple, but is it obviously correct? I don't know. But it's well tested. It has 600 lines of code of tests, which should give us some confidence to say, yeah, this function works really well. And if we look at these tests in detail, even we see that there's lots of different types applied. We have integers, we have some floating point numbers here. We even have rational numbers, which even for our standards, this is quite rare to actually test with them, which is a good sign. And even these human edge cases where we say 0.1, famously not representable as a floating point number because it's not an exact power of 2, even those are tested. And then we come to these integer test cases here at the bottom where even our type max edge cases are tested. Sounds really, really good. But then we notice also there's lots of hard-coded values. And we usually want to avoid hard-coded values in our code. So why do we now put them into our tests? Maybe something to think about for a minute. And this always makes me think, did we miss anything? Because it's suspicious, right? There's like 600 lines of code, and I'm talking about this here, and there's hard-coded values, so maybe there's something here. So let's look at the docs again and say, can we extract something about it and think about, hey, can we use some technique to maybe test it a little bit? And what I found for this is property-based testing, and maybe some of you know it already because it's 26 years old. It's initially introduced in QuickCheck in Haskell in 1999. There's lots of variations on this idea. There's many improvements since then, since the initial introduction. There's coverage guidance that has come into being. And the general idea is that you generate some random, well-structured input and use it as test input for some interesting properties about your functions. And when you see a failure in this case, well, you can be reasonably confident that something is actually going wrong. Now, there's lots of packages that implement this in other languages. Also in Julia, there's lots of Julia ports of QuickCheck. In Python, for example, there's the wonderful hypothesis package. In C++, there's Google fuzz testing, which combines this property-based testing approach with fuzzing. Maybe some of you know this from a security point of view. In Rust, there's prop test, which basically is the same thing here. And there's lots and lots of many different packages that have very different capabilities sometimes. And well, let's just get right into it and try to define some properties for Julia. So going back to our floor division function, what can we immediately see here just from this very short doc string? Well, one of the first things we might want to notice is this less than or equal, right? And we should immediately be able to say, hey, our floor division should be less than or equal the division, right? That's something we might want to reasonably extract here. And in fact, we can do that. And there's more than that, because we also say, hey, it's an integer. And in base, there's this nifty little function is integer, which does nothing more than tell us if the number that we put in is an integer. There's no fractional part remaining, and it's just saying, hey, when I convert this to some integer of a large enough data type, I would not get an error. And there's a third trickier property we could actually extract here, and that is the largest integer. And well, for the division here, there's two cases. Either the division itself is already an integer, then we just want to get that exact integer because it's the largest integer less than or equal to the division. And if it's not an integer, then we can say, okay, the floor division has to sandwich the proper division. So it has to be the next smallest and next largest integer other than the proper division. So we have properties. We've got one part of the property-based testing. Now we want to randomize some inputs, and this is basically what my talk is now going to be about from now on. It's Supposition.jl. It's a package that I've created a few years ago. It's heavily inspired by the Python package Hypothesis, because I've looked at multiple different approaches over the years, and I've settled on this as being my favorite so far. And its job in all this property-based testing is generating and minimizing inputs in a somewhat user-friendly way. It's very compatible with test.jl and testitem.jl. So you should, in principle, be able to just take it and use it in your existing test framework and test setups. So please do that. It's user extensible, so you can define your own generators, your own kind of randomizations, that kind of thing. And if you use it, you get to use this fancy badge that I've designed. So you can be very proud of it if you do find some bugs with it. And I personally consider a bad user experience in this package a bug. So if you have a problem with it and don't like it, please do tell me about it. Now, how do we actually do this? First of all, well, using supposition, of course. And finally, well, we need to be able to say, okay, we want to generate some data. And for our floor division, we're just going to say, okay, let's just use the floating points because we know there's some trickiness with floating points always. These are kind of tricky little guys. And this data.floats, this is a rich object that can say, hey, I give you all kinds of different data. I give you 16-bit floating points, I give you 32-bit floating points, 64 bits, infinities, all kinds of non-bit patterns, quiet nulls, signaling nulls, everything. This thing will generate anything that you could possibly think of for floating points. And of course, you can create and compose your own, and we will get to that in a little bit. So now let's just try it out. We say, okay, we want our floor division, one of our floor division properties. In this case, the floor division should be less than or equal to the proper division. And we say, okay, we want to check this. This is the main interface you would want to use here. And you just give it this existing property and pass as arguments this generator that we've defined. This floating point generator that gives us these random numbers. And if we execute this, some of you may see this already coming, we get a bug. Maybe it's a bug. We found a counterexample at least. And in this case, if you say, okay, the arguments are 0 and 0, well, anyone familiar with floating point can tell you this is probably because of nuns. And indeed, dividing by 0 is a none in this case. And well, we say we always return an integer, but we kind of got this coming for us because we didn't filter anything out. So let's do that. We just say, okay, we want only some floating point numbers, and we can say we don't want infinities because they're not going to be anything well behaved. We don't want nuns; these are not going to be well behaved either. And for the second argument, we definitely want to say there's no zeros because if you divide by zeros, we get nastiness yet again. So let's just filter that out. And this filter expression here, we just get a new generator that's composed from the original one. And if we put this now in, we still get a bug. That's curious. So what's going on here? Is this just one case here? Well, if we try it out, let's see, we get 744 and 743.5. So yes, it's definitely wrong because we said we wanted to be less than or equal and suddenly we're larger. But unfortunately, this is not just one case. Every single dot here is either where the floor division is wrong or the ceiling division is wrong. And you might see this is a lot, but this is just for float 16. This is about 0.05% of all floating point 16s. So I guess we can reasonably say that the simple function does not mean that a bug-free function. So maybe we should look at some things more closely. And this function in particular is luckily already well tested, and this is already a known bug, so I haven't revealed anything that's unknown so far. It's unfortunately difficult to fix because for some divisions you need higher precision, and in some cases to get that precision you would potentially have to go to big float, which is a big performance loss as well. So it's an ongoing discussion there, and we've decided to say, okay, let's for now track this in this correctness bug label, and there's a number of them on the issue tracker now, and we're slowly getting to the state where we can say, okay, we can fix more of these things, and we want to fix more of these things because it's not really that good for us. And for integers, it's correct, except for the division by 0, which throws an error, but again, this is kind of to be expected here. Okay, enough about floating point. Let's look at these mutually inverse functions that I've promised earlier. Some of them are maybe well known, some of them are not well known, but I think the ones that are probably most well known to almost everyone here is these string and parse functions. You know, we have these stringify functions that say, okay, we give an integer and a number base, and we want to get a string back out of that integer in that number base. And the inverse of that is the parsing function, where we give it a type and that string as well as its base, and it gives us back the integer that we wanted to originally stringify. And there's also this caveat at the bottom here where it says, hey, if the string does not contain a valid number, an error is raised. So this at least warns us, hey, something is can potentially go wrong if you put the wrong thing in, which is already good. So okay, we want to say mutually inverse stuff. How can we test this? Well, we do the same thing. We generate some random input and just throw it at it and see if it breaks, which is the most comfortable way of doing it. So we just pick some number. I've only picked the positive integers here because it makes the property a little bit easier to think about. And for the base, well, I've already done some preemptive testing and have determined, well, the allowed bases are from 2 to 62 inclusive. The other bases are not allowed. Curiously, the same numbers negative also work, but this doesn't imply anything, unfortunately. So if we want to say, we want to do the round trip testing here that I've mentioned, this, because these are inverses of each other, we can just say, okay, let's stringify the function in the in its base, and then parse it back and say, is this equal to what we originally generated? And yes, this works. Wonderful. But this was only one direction, because we can also do the other thing, of course. We can say we want to generate a string, and then we want to parse it first, stringify the result, and compare it to the original string. And well, let's just say, okay, let's define some alphabet that we presume this function uses because it wasn't documented. And in this case, we just say, okay, it's the numbers first, and the lowercase letters followed by the uppercase letters, which 10 and 62 and 10 and 26 and 26 makes 62. So this sounds like a reasonable guess. And we have to adjust our function a little bit because we have now an interdependency in the generation here, but don't worry about the details. In the end, we really just say parse this string as an integer in the base that we wanted to use as an input, stringify it again, and compare the strings. And well, if we now run this, we do get something. So we get this curious argument error about an invalid base 37-digit lowercase b in the string lowercase b. And this is where the minimization comes in. If we just generate random input, we would have gotten huge strings. So supposition minimizing this to a small example is already very useful for us. And if we parse this int, this string lowercase b in a different base, we don't get an error? Huh. Well, how about that? Is this now a bug? You can vote as well if you want. Oh, no one is brave enough. Okay. Well, it turns out it's not a bug. It's just that the string and parse function, once they cross 36, the base 36, they change the alphabet underneath of you. And so if we take this into account for our property and use it differently, we can say that it's actually correct. These are inverses of each other. They're just behaving in an unexpected way, which is the case that I mentioned in the beginning. We read some source code, think it's odd, and suddenly we think, well, I guess I have misunderstood something, or we should document this maybe properly better. Either way, this is something I had to change yesterday in my slides because I only noticed it yesterday. So sometimes the fault is with us. Let's not jump to a conclusion, but go to a conclusion in a sense. And I guess we can agree that correctness is really, really hard. And I don't know how to say this differently, but hidden assumptions are everywhere. Sometimes they're in our documentation, in our code. Sometimes they're in our heads when we read something and assume how things work. Like I assumed that the alphabet was used consistently in some different way. Don't assume that you found all the edge cases, even if it's very well tested, because this parse and string code as well, it's tested in exactly the same way. It's well tested. It's just not documented that it's doing that, right? So that's something that we can work on, and it's something that I will open a pull request later today in the hackathon. Try to find these good properties that you want your algorithm to have, or your code to have, and document them. Because this is something that, as a user, is very, very valuable to actually say, hey, if I can trust that the documentation and what it's saying is correct, then I can confidently say, okay, I don't need to check further, and I can say, okay, in the worst case, I can say I can stop this out completely and say, hey, I know now what I have to uphold to be able to test my things, maybe with something that's less memory intensive. And property-based testing can help in this regard because it forces you to think about all different kinds of inputs. And if you don't think about something and you miss something, the computer will tell you, hey, you've missed something, which is very helpful because I forget things all the time. So for me, the computer is really something that I can say, hey, it keeps me accountable to myself. Also check out, please, the Supposition.jl documentation. I have a whole page just listing resources for property-based testing if you need more information. I will also be here for the remainder of the day, of course. You can answer me questions all the time about it. I love it. And yeah, for the future, there's, of course, stuff that Supposition.jl cannot do for you, for example. Technically, we can test state machines with it. It's quite ugly, and I don't like it. and I want to improve the UX for this because it's a bit unwieldy and it should be better. I also want to implement some test isolation in new processes, because sometimes when you say, hey, I want to test against the C implementation, and then the C implementation seg faults, what are you gonna do? Your entire test case is now gone. You can't do anything about it. I want to provide more default possibility, and on main, for example, there's something that generates matrices, just bare matrices, but it's probably of interest for all the scientists here. And I want to give some opportunity to customize the steering of this shrinking behavior, where we can say, okay, I'm only interested in certain kinds of behavior, or I know that there's a better heuristic or something, because the defaults are very good, but they're not perfect for every use case, of course. Now, that's as far as supposition can improve. How can Julia improve, and how does it already improve? I would love it if we had some facilities for managing or scheduling tasks, because if I can sort of stop this out or remove this from the Julia runtime, I can control it, and this means I can potentially catch some race conditions. Rust has similar projects with its async code, and they can do this kind of thing, and I would love to do it in Julia as well. I want better reflection, because I want to know, hey, what are the actual functions that call the special new function in a struct? Because this is where really the boundary lies, what a struct is enforcing. And if I can directly find these and generate these automatically, it makes my life much easier, because you don't have to customize everything. I want coverage information at runtime, because then I can do coverage guided generation of the inputs to maybe hit some special branches that are rare to hit otherwise and difficult to find. And where the area where we should improve more, and where we are improving, is of course our documentation. And a huge shout out to these 3 amazing people here. Yesterday we've already heard about the fold and map reduce refactor and how important that is. Huge shout out to Matt for this. I love it. Please more of this, and please merge it as soon as possible. Huge shout out also to Jakob Nissen at Jackney on Discourse and Zulip and Slack, and he's currently investigating the I/O semantics, which are a little bit sketchy, I say, but that's for him to delve deeper into. And also a big shout out to Andy Dienes, who's been over the last few weeks incessantly finding more and more things and fixing more and more things about tricky edge cases, specifically with type max in various functions. And yeah. That concludes my talk. Any questions?
Thank you for the talk. So if you have some questions.
Thanks. Hi, nice talk. Where's the randomness you mentioned?
Where's the randomness? Well, it's hidden behind the @check macro, and it's handling all that under the hood for you. And the reason for that is very simple. It's on the very next slide. If you don't do it, you throw 100,000 floating point numbers that you generate randomly at it, and it passes. And the question is, why does it pass? Well, run, for one, only generates in the half-open interval from 0 to 1, excluding the 1. So we would not find this weird edge case with the negative 32 point something. And that's why this whole generation process is hidden a little bit. It's a little bit unfortunate, because, of course, it makes it feel more magical, but this is really necessary so that generation and shrinking can interact with each other in a well-defined manner, and that it can do this properly.
Okay, I see. And so as a follow-up question, do you kind of have a way to choose a random seed, but then report it later so that the failing test is reproducible?
Yes, this is a very core feature. You can give it an RNG that you want to use. It also generates a database of previously failing examples and tries to reuse them when you run it again. Just so, for one, you don't waste time. If it's a long-running property, you can say, okay, I have a failing example, I want to reuse this. It's a little bit broken at the moment. Windows has name limitations, and yeah, I want to change it as well. I just haven't gotten the time for that yet.
Hello, thanks for the great talk. Why did it start with 0 in the first test?
You mean let's see, this you mean, right? Well, supposition is a little bit smart, and it knows, hey, floating points can sometimes have issues with zeros. So it immediately, when it finds some counterexample, it immediately tries, does it also fail with 0? Because it's a very obvious thing that can happen. It's a very obvious edge case, and these kinds of edge cases are important to test first, because those are likely where some bugs are.
Thank you for the talk. I wanted to ask about the scheduling of tasks and testing there. Is that something you envision belonging in a package like Supposition.jl, or beyond as kind of a, and as a second part, is what you envision something like specific marching between tasks and scheduling to create those race conditions? Or can you speak to that a little bit?
What I would envision for it, what I would hope from base is that I get some mechanism to be able to say, hey, you want to schedule a set of tasks. Here's these tasks. It's your responsibility to schedule them now, and you can do that in whatever way you want. This is something that that I would need. Specifically, the area that I miss from base, where I cannot just hold it on top at the moment, is saying, hey, when a task has been paused and resumes, I have no control over this at the moment, and this means that I cannot really say, okay, if there's some I/O that happens and it resumes afterwards, I cannot say, okay, no, you don't resume yet. Something else gets to run first, right? Because this is where also an area where race conditions can happen quite often, and this is something I just cannot do at the moment. I have a blog post about a similar topic here. I can show it to you later. But this is an area where I would really say, hey, just give me the ability to schedule something freely in whatever way I want, especially when it's being resumed.
Okay, we have time for a quick last question.
I've got one question about code coverage and moving into branches. Do you do any code analysis to go like backtrack coming from the branches? Which input do you need so that
sorry,
you go?
Could you repeat the question? It's very quiet.
Sorry. So do you do any like if you want to go to any branches, like have code coverage in every branches, do you do any backtracking to get the input that you need, that you go into the branch so that you have like 100% test coverage?
So at the moment, Supposition does not track coverage at all. It doesn't know anything about it because I can't get this information at runtime. I would assume if I had this information, I would maybe do some cross analysis between the stuff we generated and say what has been executed there. I don't know how intensive this would be, but the first step would really be needed, that I need access to the coverage information.
Okay, we can thank again the speaker.